here the remaining slides and the contents of the textbook will provide you as a reference. And I would recommend you for whatever the system you're going to model in the future, you can refer to the slides and the textbook. And you can always find certain primitive forms from our textbook to extend your work. For the electrical systems, the three basic components are the resistors, capacitors, and inductors. And those are the formulations. The voltage across the two nodes of the resistors equal to Ri. I is the current. Again, for C times the derivative of the voltage equal to I. So, which means if you wish to, well, you know the capacitor basically is a gap. And if you have been disassembled capacitors, you basically see there's a two plates, and in between there's either a space or they filled up certain material to increase the capacitance. Either way, okay. So basically, this is the how to say. If you don't have anything, basically this is open gate. So if you want to have anything to produce, say current produced, then you better to do it is to change, to apply the voltage is time varying. So that's the principle we take up here. For any time varying voltage, and then you will see the current. If you apply is a DC voltage across the capacitors, basically is you are charging the capacitors. Okay, you are charging, but you don't have any current. Okay. These are inductors. Inductors is taking up this format. If you want to have the effection, then you have to use the time varying current. And in electrical engineering, most of the if you like to have an analog, you can analog to this. This component will be similar to mass. This one will be similar to damping component. This will be similar to spring. If you like to have that kind of the analogy, then it will be a good way. Okay. So the three basic components plus two laws, and this is we call the Kirchhoff whatever the laws or theory. So the first one is that at any node, the current should be conserved. It's no depletion, no addition. So which means the incoming current will be equal to the summation of the outgoing. The second one is for any closed loop, the voltage should be conserved. So for example, if you follow up this one, then the voltage from here to here should be 0. Okay, so basically we have the three basic equations and two laws. We should be able to derive everything here. And that depends on how we look at the systems. So for example here, quickly do this one here. So for this formulation, basically here, this is the node at this node at this here. So for example, you could imagine this is one loop. Okay. So using that loop, then we can use the loop law here. So basically here, the V1 will be equal to the voltage drop across the two things, just like this. And again, you look at this loop, a second loop, then basically the voltage drop from here should be equal to the voltage drop from here to here. That go to here. So here I have individually applied the voltage drop or the current, the principle from the three basic and to here. And so once we have the basic information, then we can apply the plus equations to see what happens. So for this equation, I can show you here is this, and that in the time domain is Ri plus the C over 1 I current integration equal to V1. So from here, if we take the Laplace transform, then we can get this, and R is constant, and let me say the Laplace of I, let me define as capital I, okay? So there's a capital I of S. So 1 over C is the coefficient that's a constant. Then here the integrations, if you remember the Laplace transform, integration of a time signal basically is equal to that signal divided by S. Okay, so again, the Laplace transform of an integral basically is transformed into 1 over S, this term. So this one should be equal to S and times yi over S. And this one, let me say the Laplace transform of V1, the lowercase V1 have the capital 1, and let me call it V1S, okay? So this is the first equation. The second equation, the same thing, the Laplace transform on that one. The second equation is 1 over C and S, I of S, and equal to V2. Okay. So we have the two equations in the S domain. In the S means complex number in the S domain. So here, for example, here is our input signal, and input, we call the input, well, the electrical engineering say this is input terminal, and this is the output terminal. So for example, this is the output, this is the input, and again, we have our transfer functions like this. If you remember, this is our output. That is our transfer function, and this is the input. For example, for this case, this is the V1, and this is the V2. So from here, we can find the ratio between the V1, V2 over V1. This is our transfer functions. And we can further derive the transfer function from here. So we can see what happens here. V2 over V1, we can derive from here. So V2 equal to, right? V2 equal to CS IS, and V1 equal to R plus CS I over X. Okay, so basically here, the I, we can cancel it, so that is becoming, if you keep the primitive terms, God bless you, is like this. Okay, you can further simplify, and we'll get this one. And here we have canceled the I here. And I is, here in other terminologies, we call the I is called the internal state variable. We will say this one later. But anyhow, this is help us to derive in this way. Okay. So that's the transfer function for this. And again, this is the time-dependent governing equations for this one. And somehow for this formulation, we somehow put into the integration. But again, if you would take the derivative, then this will be derivative, then this will be I, this will be derivative. So basically, this is each of these equations are the equivalent description of certain differential equations. Okay, so that is exactly, in terms of the mathematics, exactly is like we did in terms of our mechanical system. This one is another example here. Okay, so would I provide to you? Okay, we can do it quickly. So again, the voltage drop here from between the two nodes, here is EI, should be equal to the voltage drop from here to here. And that composes of the three components here. Okay, so that is the first loop. The second loop, again, the voltage drop between the two nodes equal to the voltage drop from here to here. And that is gone to here. So in a similar way, we can derive the input-output relation as a transfer function there. So here I leave to you for your exercise. Another component is called the operational amplifier, and people just call it op amp. And this one basically is composed of the diode, the PN junction, the PN photodiode, and you should have learned that one from ES 307, right? Photodiode,
No, I don't think
PN
so.
junction, no. Okay, so that's okay. So you just know there's a name, there's a electronic component we call PN junction or photodiode. The PN junction, the PN diode is just PN diode. Okay, if you're going to use that one, then for that component, the primitive Gaussian equation is described by this. To use the diode, you have to set up in this way. Okay, the manufacturers provide a data sheet and give you the suggestions how to use this component. So usually in the data sheet, it will provide you a few kind of circuits and show you how to use it. And this is a common one. So if you want to use this one, basically there's a two input E1, E2, and this is the output here. And somehow here you have to link into the ground here. So the output equal to the difference of E2, E1 multiplied with K. K is called the differential gain. Basically, K usually is greater than 1. And the larger the number K, here, that's the reason why we call the amplifiers. The K is larger than 1. We try to amplify the input signal to get to the output here. Okay. And so, for example, say in my current research, I try to detect a very weak light. And that kind of light basically is in terms of the photons, very, very weak light intensity. So I detect that one, then the current converted from the sensors and is way too small. And I want to take up the detected signal in terms of current and feed it into computer for further action. And you know the computer right now, the PC, desktop, or whatever, they can take up its voltage is either the zero, in the 3 voltage or into the 5 voltage range, and the current is about the milliamps. If you couldn't fit into that kind of range, then basically your computer won't be able to read it or have a problem to take up signals. So for example, right now I have detected the light, and the output of the sensor is so weak in terms of current. So the next stage, right now I'm hiring 2 electrical engineering students to help me to develop an the op-amp circuit. In a way, I ask them, okay, here is a signal. I will ask you to give me the amplification such that the signal can be amplified and then feed into the PC. So they take up this one. So basically using this principle and composed of other supporting circuits I don't know. But basically I want to say, I give them my requirement is I want to have the signal be able to read by the PC, but also I don't want you to amplify the noise. You only amplify the signal but not noise. Okay, so that is the kind of here I just show you one example here. Okay, so next page we might have here. This is the typical amplifier, and the previous one is open loop, the op-amp. This one we have the closed loop. Basically here is the output terminal. Here we connect resistors, try to get the feedback of the signal to the input here. So basically here has a little closed loop here. And here we added up the additional, we call the input resistance here. So by modulating the R1 and R2, we should be able to do something. And then here, that is our for these operations, for this kind of layout, again, this layout is suggested by a vendor. Okay, this is a very standard, very typical circuit for op-amp applications. So for this one, the output input will be equal to the ratio of the two resistors. So that gives us a very easy to say, hey, if I want to amplify the output, the signal, say 2000, I simply take the ratio of the two resistors in the 2000, then pretty much I can achieve my work. And the remaining issue is, okay, we can do this one. The remaining issue is how to get rid of the noise signal, not to amplify in this way. So that is they doing right now. Okay. Here is a follow-up is a few slides, and that is from our textbook for the tape. So basically here we have a few applications and few scenarios, and they might have resistors or components, and then they have the different circuits connections. So here just provide for your reference. And okay, a few slides here, let me quickly go over those things. And again, those are the very common practice, and you just pick one. So let me go over this one very quickly, and then go to the another topic, go to fluid system. Most of the time when we work in the project, and for mechanical engineers, most of the time is will work with electrical or other discipline, basically work as a team. Okay, and it's really impossible to have one in 4 years to know the two disciplines so well. So basically work as a team. But gradually, hopefully you accumulate your experience, and then a few years later you should be able to do general tasks in other background. Yeah. So this is a fluid system. And fluid system, basically here we are taking care of is the one is we call the resistance, the fluid resistance, the flow resistance here. For example, if this is a pipe, and this is called the pipe flow, and we know for fluid to flow through the pipe, we need to apply the pressure. If you have heard they call the pressure head, right? The basic pressure head is tell you the equivalent quantity of the pressure between the two nodes. If there would be no pressure head, or there's a no pressure difference here, basically the fluid will sit there without movement. So that is piece of cake right now for you. And for steady state fluid flow in a pipe, and if you remember in your fluid mechanics, you should remember this is called the Hagen principle or Hagen theory. Yeah, right? So that basically is saying is the pressure difference is equal to, there's quite a few forms. All the forms are equivalent. Here I pick one is this. Assuming the pipe has the diameter capital D, and the length of the traveling you concerned is L, and the mu is called the dynamic viscosity. Okay, and here viscosity have two kinds. One is static, one is dynamic. Here you have to pick a dynamic. So under these situations, then those are the fluid properties and geometry of the pipe, and this is the flow, the fluid flow, and fluid flow in the unit of say the speed per second. But many times people like to do it is using the volume rate. Okay, so anyhow, this is the supplied the pressures difference, and this is fluid flow. Then this one you have to govern by this equation here. This one can be derived from a Bernoulli's equation easily. But here, let me skip all those kind of portions. So here, if we define these coefficients as R, so basically this equivalent to this is our power source. And this is our flow signal. And here, we simply define as the flow resistance here. With this concept, then we can try to formulate this basically is the toilet kind of the reservoir example here. For this simple example, we can see is, for example, here the setup is here. We have the input. The Q is called the if you like, you can take a note. The Q is the flow rate. Here, the Q is the flow rate. The flow is in terms of the volume per time. Okay. So here is the input of the volume rate, and here is the discharge, the output volume rate. And those will be governed by the input and the geometry here. Then we can formulate is this. You can see right now the formulation is this. The formulation of the equation is this. The net of the accumulation, the net accumulation of the fluid in this reservoir is equal to the input minus output, right? For example, if this input is greater than the output, then this will gradually accumulate, elevated. Vice versa, this will deplete gradually. So basically, the volume rate difference will give us the accumulation in the reservoir. The reservoir, basically, in terms of time, is the cross-sectional area multiplied with the change in height, the time rate of the change in height. Okay. So under these situations, then we can plug in all the informations. And for example, here, let me plug in the output here. Let me formulate further the output here. Basically, assuming here we have such pipeline here, we have such pipelines here. So the output can be related to the pressure between the 2 points here. So again, this is the inlet pressure, this is the outlet pressure here, and equivalently delta P, according to here, this model of this portion can be applied to here. So here the pressure is let me call this pressure is P, let me call this pressure is PA. So P minus PA basically equal to the resistance put in this pipe and multiply with the flow. Okay. So under these situations, and then also for this P, pressure at the outlet equal to PA. Okay. So for this P here, this is the inlet pressure of this pipe. This P equivalent is at the bottom of the reservoir. So basically the P equal to rho G times H. So here we plug in everything. So this is a governing equation. From this governing equation, basically it's governed by the change in height, H. The only variable here we have, the only independent variable here is H. So basically this is the first order differential equations in terms of H. The A is the geometry given. This Qing is the input you can command, you can design, and everything others are the material properties. Okay, so that is a very quick example here. We also have I think the textbook also mentioned other modeling, like I look at the contents if you have time. That pretty much is like the gear set, helical gears, something like this one. Those things will be from your ME 302, the machine designs. Okay, and so for those things I will skip, and also they have other topic I didn't cover here. It's about the thermal systems. Heat transfer basically is in terms of conductance, convection. Radiation is very rare to see in controls unless you do the space radiation, the space energy, solar energy. And so here I don't cover the thermal system, but in textbook they have a few pages. They kind of cover this one. So again, in these sections, it's not our focus in control, but I would say those information together with your other textbooks in other topic will be the references for whatever the system you're going to work on. Okay. Most of the time,